Chapter 4, Plate Tectonics. Today we're going to look at Science and Santa Claus, Continental Drift, Evidence from the Seafloor, Plate Tectonics, and Plate Boundaries. Science and Santa Claus is a paradigm which models or patterns for thinking about or valuing a situation. A paradigm shift is a fundamental change in an accepted view or understanding of a concept. Thus, why we're talking about Santa Claus in earth science. Think of when you were a child, you may have considered Santa Claus to be the source of your Christmas presents. Then later on, you find out that your parents were actually the source, and your paradigm has changed. You have had a paradigm shift. Which brings us to earth science, where plate tectonics represents a paradigm shift in our view of the earth and how it works. The change of views actually occurred over several decades, where Earth's surface is divided into two major elevation zones: land and shallow oceans, and the deep ocean floor. Then there's continental drift. The early 20th century paradigm was the contracting Earth. The planet is slowly cooling and contracting as heat of formation is lost. The mountains represent the wrinkles formed by the contraction of the surface. The collapse of the surface formed the ocean basins. The continents and the oceans were effectively fixed in place, and the vertical crustal movements dominated. Continental drift is the paradigm shift. Laurasia and Gondwana. The continental drift. Most modern continents had formed by 65 million years ago. Wegener's alternative paradigm is that continental drift is actually occurring, where the continents have occupied different locations on Earth's surface in geologic past. For instance, 250 million years ago, the continents were all together in a supercontinent called Pangaea. The continents drifted across the surface of the Earth to their present locations, and they're actually still drifting. Wegener observed that there were matching features of the different continents. Notice here how this is Pangaea all together, and then you can see there's Africa and how South America kind of fits in here, and Australia fits in there. Another observation that he made was the fossil distribution. See right here, you can tell that this brown area shows fossils in Africa when Pangaea was connected, before these two continents actually separated. The same types of animals lived here. Therefore, there would be fossils on both continents in sort of the same place. Same thing down here toward the south part of Africa and South America, and another section here where the fossils are the same. Here's another place where this occurred. It's not just Africa and South America. It would be India and Antarctica and Australia. The matching features. A continuous mountain belt can be formed when Pangaea is reassembled. Here, you can match the mountain belts among North America, Europe, and Greenland. Matching features as well. The opposing edges of continents actually fit together along the shallow continental shelf. There's also unusual rock sequences that match between Africa and South America. Paleoclimates. The evidence of a thick ice sheet throughout the southern continents. Rocks formed into tropical conditions, for example, coal swamps in North America, which is near the equator. Glacial features. The arrows indicate the direction of ice movement, which was determined by the striations or grooves cut by the glaciers. If you've ever been in an area where a glacier has melted, you can actually see where the glacier made these striations in the land. It's quite interesting. Wegener's continental drift hypothesis was not widely accepted at the time because he was considered an outsider among geologists, and his use of deductive reasoning was considered very unusual for the time. He could not explain how the continents moved. Therefore, people thought, well, since he can't explain how they move, then of course they don't. Supporters of the contracting Earth hypothesis came up with alternative explanations for some of Wegener's observations. For example, the land bridges allowed fossil organisms to move between continents. In the decades following Wegener's research, key observations about the seafloor contributed to a new understanding of Earth processes. The seafloor topography, the age of the seafloor, heat flow, volcanoes, and earthquakes. There's evidence from the seafloor. We're going to go into this a little bit. Take a look here. This is the United States and the eastern coast. Here's the continental shelf where the ocean gets significantly deeper here, and it goes way down. Here's Bermuda, which is the top of a mountain that's under the ocean. The abysmal plain, very deep. And here's another deep part of the ocean. The bottom of the ocean is not smooth. It's more like there's mountains there, and there are valleys there. Seafloor topography. Key features: the continental shelf, which is the narrow, shallow ocean surrounding the continents. The abysmal plain, which we just looked at. Relatively level seafloor, like a valley, often with volcanoes, like Bermuda. There are ocean ridges. Submarine mountain ranges. That's a source of volcanic activity. And they might even reach the surface, such as in Iceland. An oceanic trench. Very deep part, like a gorge or a fjord on land. The deepest portion of ocean floor is the Puerto Rican Trench. There's evidence from the seafloor. The ocean ridges. The ocean ridge system occupies much of the seafloor in all the world's ocean basins, often found toward the center of oceans. Found adjacent to some of the continents or island chains and along the margins of oceans, they're most common around the Pacific Ocean. These trenches around the Pacific Ocean. I wonder. Look, the Mariana Trench is in the Pacific Ocean. Here's the other side of the Pacific Ocean. And also the Ring of Fire. Keep that phrase in mind as we go into other topics. The age of the ocean floor. How old is it? Well, the age of the seafloor rocks varies systematically. The rocks of the seafloor are very young compared to most rocks that are on the continent. Rocks on the ocean floor are younger than 200 million years old, and rocks on the continent are as old as 4,000 million years old. That's quite a difference. Heat flow, volcanoes, and earthquakes. They're all related. Heat flow varies systematically around the world. It's highest along the oceanic ridges, and it's lowest on continents and in the ocean far from the ridges. Evidence from the seafloor. There's a lot of activity where these little red dots are. The most active volcanoes located around the Pacific Rim near the trenches, which is called the Ring of Fire. Most active volcanoes are found near the oceanic trenches. Let's take a look at that again. The Ring of Fire, which continues over here. There's a lot of earthquakes and volcanic activity along the Ring of Fire. And here's the other side of it. Earthquakes. That's what these little yellow dots represent. These are the earthquakes that occurred during 2005. They're found near ocean ridges and trenches. Earthquakes are recorded up to 800 kilometers in depth. Deep earthquakes are found only near oceanic trenches. The largest earthquakes are found near the trenches. Now here's a side cut that shows shallow earthquakes to deeper earthquakes. The earthquakes become deeper with distance from the trenches. So the farther away they are, the deeper they are. They often occur in association with volcanoes. So continental volcanoes, here's the continent. Here's the ocean. Here's the Wadati-Benioff zone, and it slopes away from the ocean. Here's the passive margin. There's no trench at the continental margin right here. The mid-oceanic ridge. A trench, which is with deep ocean floor right here, like the Mariana Trench would be right along here. Continental volcanoes near the trenches. Seafloor spreading hypothesis. Here are the observations. Ocean margins without trenches have older seafloor, no volcanoes or earthquakes. Ocean ridges have high heat flow, young rocks, and elevated seafloor. Ocean margins with a trench have older seafloor, volcanism, and earthquakes. Harry Hess first proposed the seafloor spreading hypothesis. He used the data he collected during World War II. Seafloor spreading hypothesis interpretations. Well, oceanic ridges, the magma rises from the mantle and forms oceanic crust and expands the seafloor, resulting in higher elevations. The seafloor moves away from the ridge like a conveyor belt, creating a gap for new material. An oceanic trench, older seafloor descends into the mantle at an active margin. The melting of rocks forms the magma and volcanism. Earthquakes are where old seafloors are consumed, And a passive margin is where the continent and the ocean transitions. Additional observations about the magnetic properties of seafloor rocks supported the seafloor spreading hypothesis. Earth has a magnetic field because it has molten rock in the outer core, heat to generate currents in the outer core, and rotation to mix the currents. Earth's magnetic field has negative and positive poles located near the north and south poles. A compass needle lines up along the lines of a magnetic force. Magnetism is when the magnetic fields force the atoms of other substances to line up with them. That's when they stick together, when all the parts are lined up, headed in the same direction. Earth's magnetic field can be defined by direction. The field points toward the magnetic poles. Inclination. The field points down in the northern hemisphere and up in the southern hemisphere. The inclination is greatest, or vertical, at the magnetic poles. The field is horizontal at the magnetic equator. The atoms in magnetic minerals align parallel to the magnetic field when magma cooled to form seafloor rocks. This preserves ancient magnetic field, or the paleomagnetism. The analysis reveals the inclination of the field where they formed, a proxy for latitude. This is the normal polarity of Earth. Earth is a big giant magnet. Notice that this is the reverse polarity. See, the arrows are pointing in from the south to the north, and here they're pointing from the north to the south, which does occur every so often, and that's called the reverse polarity. The magnetic field reverses about every 250,000 years, and we're about due for a change very soon. The longest is tens of millions of years, and the shortest is tens of thousands of years. Few thousand years to change the polarity. The paleomagnetism and seafloor spreading. And they can tell by how the particles line up within the substances how often the magnetism reversed. Normal polarity rocks currently forming from magma along the oceanic ridge. The marine surveys measure the strength of Earth's magnetic field, and the strength is higher in regions of normal polarity and lower where there's a reverse polarity. The polarity of seafloor alternates between normal and reverse on either side of the oceanic ridge. Of course it would, because they're all pointing in the same direction. The symmetrical pattern on either side of the ridge. There are stripes of similar width and polarity. The polarity of the seafloor alternates between normal and reverse on either side of the ocean ridge. Here's a diagram of a cross-section of the ocean floor showing the magnetic pattern that's interpreted as having been produced by belts of basalt. The younger is moving upward, and the older is flowing sideways. Of course, this doesn't happen, very quickly. We're talking about the plates and the seafloor and rocks moving. We're talking thousands and millions of years. The Earth has three compositional layers: the crust, the mantle, and the core. The crust being the outer surface, and the mantle the between the core and the crust. And the core is in the center. Here's the center, the mantle and the crust. Two key layers in the crust and upper mantle are the lithosphere and the asthenosphere. Lithosphere is a rigid layer composed of crust and uppermost mantle, and it's divided into mobile tectonic plates, meaning they move. The asthenosphere is the weaker layer found in the upper part of the mantle. The flows are due to small proportion, about 1%, of melted minerals. The plates of the world. There's a rigid lithosphere and it's divided into mobile tectonic plates. I know you've heard that term before. Tectonic plates do not represent continents. Now, they do contain continents, but they're not just the continent themselves. The interaction of the plates along their boundaries account for the formation of new lithosphere, earthquakes, volcanoes, and the gradual movement of the continents, known as Continental Drift. Many of these processes involve the melting of rocks. The melting of rocks produce magma associated with the formation of lithosphere at oceanic ridges and the generation of volcanoes near oceanic trenches. Three changes lead to partial melting: increasing temperature, decreasing pressure, and the addition of water. The melting of rocks is critical to the process of plate tectonics. And the next 4 slides show why rocks melt. Now, they only melt partially. They don't become total liquid. This particular slide shows how the melting is due to increasing temperature. The closer you get to the magma, the warmer it is. And the closer it is, the more it melts. The temperature increases with depth, but the increasing pressure actually impedes the melting process. The closer to the magma you are, the hotter it is. Now here it shows how the melting is due to increased pressure. The decompression melting occurs as rocks rise toward the surface. An example of this would be what occurs below ocean ridges. There's no melting at the X before the addition of water, but when water is added, the chemical reactions in the presence of water lowers the temperature that's necessary for the melting of some of the minerals. The melting occurs where the X is in this graph after the addition of water. The formation of new lithosphere at oceanic ridges. The new oceanic lithosphere is added along the edges of 2 plates that move away from the ridge. Lithosphere is formed from magma, which is generated by the decompression melting of the asthenosphere. The continental lithosphere is not consumed in subduction, the generation of earthquakes and volcanoes. The continental lithosphere is not consumed in subduction zones. Continents can break up or combine, but the total volume remains the same. It can't just disappear. The older lithosphere is destroyed at subduction zone to balance the formation of new material. Earthquakes occur from the surface to a depth of 800 kilometers in descending plate. That's the plate that goes under. The rate of movement, Kauai formed about 5 million years ago, and it has moved 600,000 meters since its formation. The Hawaiian Islands form over a hot spot in the Pacific Ocean. It's interesting that this is one of the oldest ones, and as the plate moved over the hot spot, you've got Kauai, you've got Oahu, you've got Molokai, Lanai, Maui. The present day hot spot is very near the Big Island, and as you know, Kilauea is still spewing lava. It has not stopped. In fact, if you were to go to the Big Island today, you could actually see lava out of the volcano. Modern satellite measurements reveal that plates move at rates of between 1 to 15 centimeters per year. The fastest rates are the Pacific and the Nazca plates, and the slowest are the Antarctic and the North American. Mantle convection cells carry hot material from Earth's interior toward the surface, and it transports cold material to depth. Two potential hypotheses interpret plate tectonics to be driven by the upper mantle or the whole mantle convection. Plate boundaries. There are three types. Divergent, meaning they're coming apart. And as the arrows show, this would be where the plate boundary is, the line in the center, and the plates would be moving apart. For example, ocean ridges. The convergent plate boundary is where the plates move toward one another. For example, in a subduction zone. And the transform boundary is where the plates are sliding past each other. For example, San Andreas Fault in California. Stages in the evolution of a divergent boundary. The continent goes under an extension, the crust gets thinner, and a rift valley forms. As the continent tears in two, the continent edges are faulted and uplifted. Basalt erupts from oceanic crust. Continental sediments blanket the subsiding margins to form continental shelves. The ocean widens and a mid-oceanic ridge develops, just like there's a mid-oceanic ridge in the Atlantic Ocean. Magma generated at a convergent boundary. The older or the colder oceanic lithosphere consumed at subduction zone. The denser plate descends down the subduction zone, just like anything else. The more dense it is, the lower it is. Water in descending plate expelled into the hot rocks of overlying mantle wedge, and the magma forms partial melting of the mantle wedge. It supplies the overlying volcanoes. At a convergent boundary, when two ocean plates collide, the older lithosphere is consumed in the subduction zone. Volcanic island arc forms behind the trench and overriding plate. An arc trench gap depends on the angle of the subduction zone. The steeper the slope, the smaller the gap. You could think of the Aleutian Islands. This concludes Chapter 4.